Hello viewers, welcome to video tutorial on potential energy and energy density. I am Dr. P. Ramakrishna, Assistant Professor of Physics, Government Degree College, Kamareddy. This concept of potential energy and energy density forms part of chapter Electrostatics in Electromagnetic Theory paper of BSc Physics syllabus. In this video tutorial, we are going to derive potential energy for system of charges and energy density in the case of continuous charge distribution. Let us have a quick recap of what we have learnt in the previous slides. That is potential, electric potential. Electric potential can be defined as work done in bringing unit positive charge from infinity to a point in the electric field. Mathematically, it can be expressed as VA is equal to W by Q naught, where VA stands for potential, electric potential at point A. It can be measured in volts, and the potential difference is expressed for 2 points in the electric fields. It is defined as amount of work done in moving unit positive charge between the 2 points in the electric field. Mathematically, it can be expressed as VA minus VB is equal to W by Q naught. Let us see the another one, that is equipotential surface. Equipotential surface can be expressed as, defined as, it is a group or collection of all such points at which the value of electric potential is same. Next thing, the relations between electric field intensity and electric potential. They are related as V is equal to minus of integral E dot dl. This is the integral form, and another one differential form, that is E is equal to minus of del V. This is gradient. Electric field intensity is the negative gradient of potential. Now let us move to the current topic, that is potential energy of system of charges. In the case of system of charges, let us consider an assembly of n number of charges, q1, q2, q3 and so on qn. For the sake of simplicity, to avoid ambiguity, we are not showing all other charges, just we are showing 4 charges, but keep it in mind that there are n number of charges. Okay, q1, q2, q3 and so on up to qn. Now let us derive equation for the potential energy of like this assembly, a system. Okay, for that what do we do? Let us calculate the work done in bringing all the charges one by one. That is, let the first charge is brought at the beginning. Then in that case, the work done will be 0. Why the work done is 0? Because no other charge is present before Q1. Okay. Now when we bring the second charge Q2, it will experience the potential due to Q1. So the work done will be equal to W1 is equal to V21 Q2. Now this relation, understand this relation, this is the work done in bringing charge Q2 into the potential of Q1, first charge. This V21 stands for potential at a position of second charge due to first charge. Remember that there may be some deviation from one textbook to other textbook, that but this is followed in the most of the text. V21 stands for potential experienced by second charge due to first charge. Now when we bring the third charge Q3, it will experience potential due to first two charges which are already present there. So the work done becomes W2 is equal to V31 Q3 plus V32 Q3. Now this is the work done against the first charge, against the field of first charge, and this is the work done against the field of second charge. Similarly, now let us assume that we are keep on adding the other n minus 1 charges. So it will form this region of interest. The highlighted region of interest is our boundary of system of n charges, n minus 1 charges. Now into this boundary, now we are bringing the last charge Qn. So it will experience potential of already present n minus 1 charges. So if we bring the last charge Qn into this field, it may be bring straight. It doesn't make any difference if it comes either straight or in a circular path or in any other zigzag path. It doesn't make any sense, any difference. So the work done is equal to Vn1 Qn and so on, Vn2 Qn and so on up to Vn n minus 1 Qn. So these are the work done. This is work done for bringing the first charge. Let us forget this first equation. The total work done will be summation of W1, W2, W3 and so on, Wn1, n minus 1. Don't confuse with this W and this W. Let us forget this equation. Okay, we are going to add from W1. So that will make the total work done. In the next slide, we are adding all these terms. Okay, we are adding all these terms and writing them in a single equation. So it will be like this. If we carefully observe the first term, this is the work done in bringing the second charge, but it is brought in the potential of only first charge. But in our assembly, that is in our system of charges, there are n number of charges. Q2 will experience the potential due to all other n minus 1 charges, isn't it? But this equation is not having all those terms. To make this equation complete, we do the movement of charges in the reverse order. We will again perform the movement of charges, but in a reverse order. Let us see. Let us see that. Again we will come back to this slide. First let us bring the last Qn charge, then followed by Qn minus 1, Qn minus 2 and so on. At the end, Q1 will come to the system of charges. Let us see. So Qn is brought. So when we bring Qn, the work done will be 0 because no other charge is present. But when we bring Qn minus 1 charge, it will experience potential of this Qn. So the work done will be W1 is equal to V n minus 1 n Q n minus 1. Okay, notice again that don't confuse. These terms are having so many subscripts, but this is the work done in bringing the charge n minus 1 charge into the field of n charge, nth charge, Qn charge. Now let us bring the n minus 2 charge. When we bring Qn minus 2, here from here it is coming, observe. So it will experience potential due to already present these two charges. So the work done will be like this. Again I am saying, don't, the equations are become tedious because of these subscript, but don't confuse, they are very simple to remember. Now like this fashion, in this way we keep on adding the charges. Let us suppose that we have added up to Q2 charges. So this is our region of interest. Already we have added n minus 1 charges starting from Qn, Qn minus 1, Qn minus 2 and so on, Q3, Q2. Now the last charge is remaining. We are bringing the last charge, that is Q1, into this region of interest. So it will experience the potential due to all other n minus 1 charges. So the work done will be written as Wn minus 1 is equal to V 1n Q1 plus V 1 n minus 1 Q1 and so on V1 to Q1. Now if we add all these terms again, as like in the previous case, we will forget this first term W is equal to 0, first equation. If you add all these equations, it will give the total work done in bringing the charges in the reverse order. Okay, now let us go back to our previous slide. That was like this. Okay, this is the work done in bringing the charges in the order of Q1, Q2, Q3 and so on up to Qn. Now we are bringing the charges in the reverse order. That is, first Qn is brought. In that case, the work done will be like this. If we observe carefully, for the second charge, Q2, in the first equation it is having only one term, but if you look in the second equation, it is having the rest of n minus 2 terms. Okay, observe here, 2n, 2n minus 1, 2n minus 2 and so on, 2, 3. That is the potential starting from third charge to nth charge is present in this equation, and the potential due to the first charge, that is before Q2, only one charge is there. Here one charge is there, potential due to one charge. Here the potential due to the remaining n minus 2 charge. Overall, we are going to have total of n minus 1 terms for each charge. So if we add up these two, we are going to get all those terms. If we add on the left side, it will become 2w. 2w is equal to, now this is the total work done in the two cases. If we observe carefully, we have separated out, we have write all the Q1 terms at one place. So if we notice, in each of the charge Q1, Q2, Qn and so on, the potential terms V1n, V1n minus 1 and so on, V12. Here V11 is missing. Similarly, in the second case, V22 will be missing. In the last case, in the same fashion, in the last case, Vnn will be missing. Okay, for nth charge. So each term is going to have, each of these terms is going to have n minus 1 potential terms. Now if we see all these things, what are all these things? These are the potentials experienced by the first charge. Similarly, these are the potentials experienced by second charge. For our simplicity, let us represent this entire thing by V1. Similarly, this as V2 and so on, this as Vn. So the equation becomes 2W is equal to V1 Q1 plus V2 Q2 plus and so on Vn Qn, or it can be written as summation of Vi Qi from I1 to n. Now if we write for W becomes half times summation of Vi Qi from I1 to n. So this is the work done in making the n number of charges into single assembly, that is to make system of n number of charges. This work will be stored in that system as a potential energy. So if anybody asks what is the potential energy of n charges, it will be like this. If we take just 3 charges, for our simplicity, if we take, we will do it at the end in question and answers. If we take only 3 charges, it will be simply W is equal to half V1 Q1 plus V2 Q2 plus V3 Q3. Okay, it can be expressed in a different fashion. So let us see how it will be at the end. Okay, remember this. So this is the potential energy of system of n charges. In order to find out the energy density, we will go to a continuous charge distribution. Here the charges were discrete. Okay, they can be identified separately. Discrete means they can be identified separately. Now let us assume that the charges, the number of charges is so large that it forms a continuous distribution. In that case, the potential energy or the work done can be represented as W is equal to half of volume integral of capital V rho V dV. Remember that this capital V is the potential and small v is the volume. Don't confuse. Okay, sometimes some of the students write this in a confusing manner. This has capital V and like that. Don't do like that. Once again I am telling, this is the potential. Capital V stands for potential, small v stands for the volume, and rho V is the volume charge density. Okay, now charge present per unit volume or total charge by total volume. Okay, volume of the distribution. Remember this equation. We are going to use this equation in the next slide. We are going to replace this rho. Observe this equation carefully. We are going to replace this rho in the next slide from Gauss law. This is the differential form of Gauss law. Gauss law can be expressed as rho is equal to del dot D. This is del operator here, and D stands for electric displacement vector. They are both of them are vectors. Here it is a dot product, scalar product of del vector and displacement vector, electric displacement. Now let us substitute this one in our earlier equation. If you substitute, it will be like this. Now we use a vector identity here. Okay, this is similar to what we have learned in vector calculus, that is del dot phi a, where phi is a scalar and a is a vector. It can be expressed as del phi dot a plus phi times del dot a. In a similar way, here instead of phi we have potential V, instead of a we have the electric displacement vector D. Okay, remember that D is vector, V is the potential. So if we write this in that fashion, it will becomes D dot del V. This is a gradient of potential. Okay, and here V del dot D. Now in the above equation we have the second term V times del dot D. So if we substitute for this term, it will be this term minus this one. So let us substitute it. Observe it carefully. Instead of V times del dot D, we have written del dot Vd minus D dot del V. Now again notice that this first term, this is a first term volume integral and also having divergence. It is volume integral of divergence of a vector. So from Gauss divergence theorem we can replace it using a surface integral. We know that from Gauss divergence theorem, surface integral of any vector is equal to volume integral of divergence of that vector. So we are replacing this with closed surface integral Vd. Again I am saying V is a scalar potential, D is a vector. Now observe this carefully. We are going to use this. Again we will reproduce the same equation here. The same equation is reproduced here. Now we are discussing this entire slide is upon this first term. Observe it carefully. So, in this expression, this one, for the point charges, in case of point charges, we know that the potential is 1 by 4 pi epsilon naught q by r for each case, each charge. So, it varies as inversely proportional to r. Similarly, electric field intensity, that is E is equal to 1 by 4 pi epsilon naught q by r square. If we write for d, epsilon naught will be missing, that is 1 by 4 pi times q by r square. But what we require here is d varies as 1 by r square. V potential is varying as 1 by r, displacement vector is varying as 1 by r square. Overall, this term Vd varies product of these two 1 by r cube. Now this term is present inside a surface integral. So if we do surface integral, surface area, we know that surface of any matter, for simplicity let us assume it as sphere 4 pi r square. So it varies as square of the radius. So overall this product will vary as 1 by r. Again I am repeating, listen to it carefully. Potential varies as 1 by r. Electric displacement vector varies as 1 by r square. So this product Vd varies as 1 by r cube. Since this product is present inside a surface integral, as surface area varies square of the radius, the total integral term, this entire term varies as 1 by r. That means if r is increasing, this term, first term will decrease. If r is decreasing, the value of term will increase. But as the charges keep on accumulating, our distribution increases. That means radius also increases. So when infinite number of charges are there, large number of charges, assembly of large number of charges, r becomes so large that sometimes we may assume it as infinity. In that case, this first term becomes 0. When r becomes infinite, this first term becomes 0. But when it is sufficiently large, when r is sufficiently large, the first term is negligible. It is almost equal to 0. Negligible, not exactly 0, but negligible, almost equal to 0. So what do? We neglect this first term. We will remain with only the second term. Let us see the second term. Now in the case of second term, W is equal to minus half integral d dot del V dv. Now you look at this term, del dot V and minus is negative gradient of potential, can be written as, yes, for electric field intensity E. So if we replace this minus del dot V, it will become d dot E. Okay, dot is here, d dot E. Now in this equation, let us replace this d with epsilon naught times E. This electric displacement vector is replaced by epsilon naught times E. In that case, the equation becomes half integral epsilon naught E square dv. Let us assume that this half times, as this is a number, numeral, it can be brought inside. So half times epsilon naught E square as some u. So entire equation becomes W is equal to volume integral of u dv. Remember that this u is called as energy density of our system of charges. where U is equal to half epsilon naught E square. Okay, energy density is equal to half epsilon naught E square. So we have derived the potential energy equation, also energy density equation. Now let us see. The energy density equation is U is equal to half epsilon naught E square. Okay. Now let us see some of the questions. As I have told, in the derivation, it is derived for potential energy is derived for n number of charges. Now let us derive it for only system of 3 charges. Okay. As we have discussed, the work done in bringing the first charge will be 0. When we bring the second charge, it will be experience potential due to already present first charge. Okay, so W2 will be Q2 V1. Similarly, W3, and if we write this one, it will be, here it is assumed that the charges are Q1, Q2 and Q3. Okay, now the distance between Q1 and Q2 is R12. So this W2 can be written as 1 by 4 pi epsilon naught times Q1 Q2 by R12. Similarly, if we bring the third charge into that assembly, so it will be W3 is equal to Q2 times V1 plus V2. If we write this in full, it will be 1 by 4 pi epsilon naught V1. This, if we expand this one, it will be Q1 Q3 by R13, and this one will be 1 by 4 pi epsilon naught Q2 Q3 by R23. Here this assembly, the assembly of the system of these charges are present in the vacuum. It is assumed that, it is not mentioned in the question, but it is assumed that they are present in the vacuum. That's why we have used epsilon naught. Now the total work done will be summation of these two terms, these two equations. So if we write this, it will be like this. Now notice that it is somewhat in a different way, but if you do some exercise, this equation will be similar to what we have derived in the previous slide, that is half summation of Qi Va. If you work out, you will get the same expression. This is, don't think that this is different, this is similar, same as half summation of Qi Va. Do it on yourself. Now these are the questions for assignment. Now here it is asked to determine potential energy of system of 3 charges of each 2 microcoulomb placed at the corner of an equilateral triangle of an arm 1 meter. Okay. Similarly, it is asked, next question is calculate energy density of electric field of intensity 1.2 into 10 to the power of 6 volt per meter. In the third question is asked in the reverse way. Here energy density is given and field intensity is asked. Fourth question is somewhat different. Here an electromagnetic region is assumed, where electric field is there as well as magnetic field is there. Magnetic energy density is mentioned and electric field intensity is given. You are supposed to find out electric field energy density due to electric field, and add it with this magnetic field. Thus will give the combined energy density of EM field. Okay, so here we will end this tutorial. In this tutorial, we have learnt about the potential energy of a system of charges as well as energy density of system of charges. In the case of energy density, it is assumed that continuous charge distribution. Thank you for watching video. Keep on watching. Thank you.